The other interesting thing is, just like force intensities are extensive properties, you remember I talked to you about this thing as measure, chunks, defined on chunks. Geometry change is also an extensive property. What I mean by that is, individual particles of a continuum have no geometrical properties. They only have location. You cannot say what's the shape of a particle. That's meaningless. But you can talk about shapes of chunks. Change in geometry of a chunk is what you can talk about. 1D shape change. Let's start with 1D because it gets us going, and our initial modeling will be done only on 1D. Okay, so what's 1D shape change? Let's say I got a bar. I mark 2 points on it, A and B. Okay, they are very close to each other. And what I do is, this bar gets deformed. When it gets deformed, it's called a rod. You know what I mean? Take a rod and you deform it. So here's the original, and then I do something to it. I pull it, stretch it, whatever. When I do that, I will get the same 2 points, A and B, which were here, are now A and B there. Okay, they have been marked, so I know that they are the same points. So now we are going to define what is meant by stretch. That is the length change intensity. The total length of this bar has changed. Can you see that? From here to here and here to here, right? But you want to say what is the intensity? Where is the length change concentrated? How concentrated is it? So what you do is you take different chunks and see how much was the length change intensity. So what we do is we measure something called stretch, which is length change intensity. That is limit as a B gets to A of this length divided by that length. If that limit lambda, and the symbol is lambda, and if the limit lambda A goes to 1, then you say there is no length change. If it goes to 0, you would say the body got crushed. If it goes to infinity, that means the body got really stretched. You with me? So it's like absolute temperature. You know what I mean? So it goes from 0 to infinity. It doesn't go from negative infinity to infinity. Okay. Now notice that I can do this for every point on this thing. I pick any random point I like. I draw a chunk. I find out where they are, and then compare this length to that length. And then I keep doing the same thing. So I can define this as a field variable. So length change intensity is a field variable. Once you got a field variable, I told you that there are many different ways of talking about it. The main ways in which we talk about this are the following. Before we go, one very important idea is that if I take this bar and I rotate it, pure rotation, you will see that lambda A will be 1. It is unaffected by rotations. It's also unaffected by translation. This must be obvious, right? So the way we get these field variables is by doing some ratio and by choosing quantities that are unaffected by rotation and translation. So they actually capture change in shape. Not change in orientation, not change in location, but change in shape. Okay. Now once you got the stretch, you can do a lot of other things which you have heard of but probably not defined in a careful way. You can define other field variables. Engineering strain, it is stretch minus 1. Okay, this is, if you look at it, it is current length over L naught minus 1, which is L minus L naught over L naught. The thing about the original definition is it was not defined as a field variable. Here it is, but it's the same idea. Engineering strain is also a field variable. But that's not the only thing you can do. The problem with all these engineering strains and things like that is that the lower limit is a finite number, but upper limit is infinity. So our typical idea is you can achieve any finite number, but you cannot achieve infinity, right? So if you take a wire, you are not thinking that you can extend it infinitely, correct? It will break before that. So clearly infinity stretching to infinity is not possible. But it looks as if stretching to 0 is possible. That is, you cannot crush things either. So a better definition, and in many cases a very useful definition, is what is called true strain, which is log of this thing, log of the stretch. But I got to tell you, there is nothing special about log. There is nothing true about true. It's just convenient. For all you know, you could have defined lambda minus 1 over lambda, and it will have exactly the same properties as true string. It will go from minus infinity to infinity, all nice things will happen. You can do that also, right? But log lambda turns out to be convenient for some purposes. Again, notice it's a matter of convenience, not a matter of truth, right? So don't think of it as something true, but log of lambda is the true string. The most convenient one is this Lagrangian string, which is half of lambda squared minus 1. So why half, why minus 1? Don't ask me those questions. You can divide it by anything. You can do 1 over 10 lambda to the 10 minus 1 if that's what works for you. But engineering string, please remember, is convenient. Why is it convenient? For all of these other things, you have to do some serious geometry and some serious power series, this, that and the other to get logarithm and all of that. What you'd like to do is get everything out of algebra. I want to do only dot product and cross product. Then this engineering string, this stretch, all of them are not convenient, but Lagrangian string is. Why is that? Because the squared helps us, because you can always write squared as dot product. So what we can do is this. I take the vector AB, dot it with itself, that will give the square of its length, divided by the vector capital AB, dot it with itself, and that will give me reference length squared. And then you can see this half is just convenient so that things work out when I take limits. Okay, so the reason for introducing Lagrangian string has to do with mathematical convenience, being able to do algebra. You will see this kind of thing shows up again in 2D and 3D. Okay, so that's the idea. Okay, now let's do next level is 2D. So in a two-dimensional shape, here's a reference shape. I've drawn a big blob, that's a reference shape. Here's a current shape. It has become a bigger, more different kind of funky looking blob. If I want to find out local changes in shape, I'll pick a point and draw two lines. That's my cross in the beginning, plus sign. Okay, and this is the point that I'm interested in, there, that point. When I deform it, locally it will become like this. So what used to be two straight lines become two kind of skewed lines. So if you want to think about it, unlike 1D lengths, here lengths, angles and orientation will change. So what used to be this way, becomes kind of like that. See what I mean? So length will change, angle will change, location will change, orientation will change. But what we are very much interested in is only shape change. We want to get rid of orientation change, and there's a very clever way of doing it, and I'll show you that in a second. So to understand how this goes to there, you can consider this like a triangle. So I'm going to draw this triangle, and then you can get a much bigger triangle. So please remember, it's not about rectangular pieces, it's about triangular pieces. So if you have taken continuum mechanics or any of these other classes, they'll spend a lot of time on talking about rectangles and parallelograms. That is not appropriate. It has to be triangles and trapezoids. And tetrahedra. So you will see what happens. Oops. So if you watch, that's a reference rectangle, and you can see it will get deformed into some kind of a funny shape. Saw that, right? So what was reference, right angle triangle, becomes a funny shape. That's the deformation. So we want to be able to see changes in shape. The way we do that is through the use of two vectors. So remember, this is my current shape, little ABC of the triangle. What I'm going to do is, I'm going to draw one line along the base, what used to be AB, and another line along this, and mark the original rectangle there. Can you see the original right angle? So now deformation intensity, deformation gradient is given by two vectors. I'm going to call it F1 vector is AB vector divided by magnitude of capital A, capital B. So this is current vector divided by original length. F2 is given by current vector AC divided by original length. And if you take the limit as B tends to A and limit as C tends to A, you will get the field variables. So these two things, F1 and F2, are field variables, and usually we write it as a matrix F, which is F1, F2, two column vectors. Right? This thing is called deformation intensity or deformation gradient vector. It's actually not deformation because it still contains aspects of rotation. Now we are going to look at how do we convert that into actual numbers, quantities that measure change in shape. So first thing is, I'm going to choose x-axis along AB, which I have done. Y-axis, the LR is perpendicular, right? So perpendicular, that's right angle. Can you see that? That's why I wrote it LR. LR means perpendicular, so I don't want to keep writing perpendicular, so I write LR to x star. So can you see this? First one is this vector, second one is that vector, and now I have a local coordinate system by which I can mark the points B and C. So notice B will be Bx comma 0 in this notation, right? And C will be Cx comma Cy. That's very nice. Now I can write down this F matrix, and now because it's with respect to this particular coordinate system, it will be called F star, the engineering stretch matrix, F star matrix equals F1, which is AB divided by magnitude of AB is Bx divided by magnitude of AB, 0, because the second component is 0, and then this will be Cx divided by magnitude of AC, and then Cy divided by magnitude of AC. Right? Notice it's an upper triangular matrix and there are exactly three components. This component, which tells you how much the body has distorted. So Cx over AC is called gamma, and that's usually called engineering shear strain. Bx over AB is called engineering axial strain. Same thing with By over AB. So these are the three things. Notice, of course, I can do a lot of things with that. For example, I can take log of this and log of this, and I will get engineering true strains. There is no meaning to taking log of that. That doesn't make sense because that can be both positive or negative. This can only be positive, so I can take log. So that's item number one. Item number two is I can do Lagrangian strain. And that is defined as F star transpose F star minus identity matrix half. Please remember, we did exactly the same thing. Why do we like Lagrangian strain? Because I can do vector algebra alone and I don't have to do all this trigonometry to compute it. At this stage, I'm not going to talk to you about the vector algebra, but take it from me that Lagrangian strain is mathematically convenient. This is geometrically and measurement wise, this is convenient. Right? And there's a simple relation between them. You can go back and forth between them because F star also has three components. Lagrangian strain will also have three components. So there's nothing new about it. Okay, that's how it works. Talk to you about